All right. I guess now it'll hold. And your name?
Dwayne.
Dwayne Lee. Yep. There you go. Bet. Okay, recorder's going. This is all still good to ready to hand out if somebody else shows up. And as some of you have noted, we have a test scheduled for today on chapter 23. So, before we get started, does anyone have any questions from chapter 23? The homework, the assignment?
Yeah.
What's that? Number 40. Beam of light enters the end of an optic fiber. Yeah, this is a good one. Everybody, who has not turned in their homework yet? None of you. Excellent. Take good notes. This is a really good exercise. Say again? No. No, you're doing it as homework, so that won't be on. Oh, something like this? Well, everything on the test is going to be out of this chapter. So the test is nothing but chapter 23. What's your name? Jacob Bettis. Boom. Thank you. All right. Here is the problem. We have an optical fiber. Now, in general, light enters at theta, and in the problem they said alpha, right? Yeah, alpha and beta. So, alpha this is beta. Which means that is gamma. And that would be some new angle theta. Cash. Tried to sneak in, didn't you?
We have a test today?
We do. So nice of you to show up for it.
Yeah, I'm done.
No, you're not. You've done your homework?
Done one of them.
Okay, well, did you do number 40? Then you'll need to take good notes because this is a really good problem. Here's the basic question that they're asking. What is the minimum index of refraction you need inside this optical fiber to guarantee you will have total internal reflection regardless of this angle alpha? Right? So we start with Snell's law. We know that N1 alpha, sine alpha. What happens when you can write faster than you can think? N1 times sine of alpha will be equal to N2 of sine beta. N1, of course, is air. This is air. And so N1 is just 1. Now, if we are trying to do this so that it doesn't matter what alpha is, then we need to solve it for the worst possible case where alpha is coming in at 90 degrees. So sine of 90 degrees times 1 will equal to the N2 times the sine of beta. But what is the sine of 90 degrees? 1. So this is 1 times 1 equals N2 sine beta, or 1 equals N sine beta. Now, we also need to know what is gamma. What is the angle gamma? Well, we can get there for a couple of ways. We can note that this is a right triangle, so beta plus gamma plus 90 degrees has to equal 180, and beta plus gamma equals 90. Or we can note that this is beta here, and since these are parallel lines, this is opposite and equal. That means that's a beta there. That angle is also beta, which tells us that beta plus gamma equals 90 degrees. Either way you go, you're going to get there. Beta plus gamma equals 90 degrees, or gamma equals 90 degrees minus beta. One second here while I look at something. Okay, now we've got another instance of Snell's law here, where we have this N2 times sine of gamma is going to be equal to, I drew that angle in the wrong place, N1 times sine of theta, where N1 is air, so the index of refraction of air is just 1, times the sine of theta. But we want to, what is our overall objective that we're starting from? We need to guarantee total internal reflection, which means that we need this to be the special case where theta equals 90 degrees. So this is 1 times the sine of 90 degrees equals 1. So once again, we have, over there we've got 1 equals N2 sine beta. Now we've got 1 equals N2 sine gamma. Okay? That means N2 sine beta must equal N2, and I'm writing too close. I'm going to start it down here. N2 sine of beta must equal N2 times sine of gamma in order to achieve total internal reflection. McGee. There you go. Still lacking Anderson, Turnage, and James Medlock. don't even remember who.
Yeah, I think he dropped out.
Oh, I'm sorry to hear that. By the way, on an unrelated note, y'all should have gotten the announcement on Canvas. If you didn't, there is apparently, you should have received by now an invitation to do an evaluation of the course. I want to encourage all of you to do it. It's not going to affect your grade one iota either way, no matter what you write or say. It's totally anonymous. I'll never know. So it is important to the university that y'all evaluate your courses. So for this course and for every other course you take, please do evaluate it. Okay? All right. So this is the condition we found that has to be achieved in order for us to ensure total internal reflection. That N2 sine of beta must equal N2 sine of gamma, which you can immediately see, you can divide out the N2, that doesn't matter. That means sine of beta must equal sine of gamma. That means beta has to equal gamma. Well, how is that possible? How is it possible for beta and gamma to be equal? Because we know that beta plus gamma must equal 90 degrees. That means if beta is equal to gamma, that means beta plus beta must also equal 90 degrees, which is just another way of saying 2 beta equals 90 degrees, or beta equals 90 degrees divided by 2 equals 45 degrees. So for internal reflection to be guaranteed, with an input angle of alpha equals 90 degrees and an exit angle of theta equals 90 degrees, which that means that beta and gamma must be equal, and they must equal 45 degrees. Okay, well, that means 1 must equal N2 times the sine of 45 degrees. Or N2, in other words, must equal 1 divided by the sine of 45 degrees, which is 1 over the square root of 2 So N2, 1 over that means you flip that back the other way. Yeah, square root of 2, right? Yeah, 1.41 something, something, something. Okay, that is the minimal internal, the minimum index of refraction necessary to ensure total internal reflection no matter what angle the incoming light enters the fiber at. All right? So, if you guarantee at least an index of refraction that's greater than or equal to the square root of 2, then any light entering the end of that fiber will be contained inside the fiber for its length until it reaches the other end. And you can't even accomplish that with full mirroring. Now, is that the whole problem? Who was it asked about this one? You did. There's a part B, isn't there? Okay, well, in that case, in air, N equals 1. In H2O, N1 equals 1.33. which means this would be 1.33 sine of 90, or 1.33 times 1, or 1.33 equals into sine beta. All the rest of this evaluation analysis still holds. Because if you'll recall, the very next thing we did was we found out that it doesn't matter what the index of refraction is, all of this is independent of that. This is the last thing that changes. Instead of 1 equals N1 equals N2 sine 45 degrees, we change that to, where can I write? 1.33 equals N2 times the sine of 45 degrees. Or now instead of 1, it's 1.33 divided by the sine of 45 degrees. Now, any more questions about that? 41. Say again?
No, I seriously don't have.
Yeah.
I mean, I have everything else.
Okay, and no, he's not. 41. A sharp image is located 391 millimeters behind a 215 millimeter focal length converging lens. Find the object distance using a ray diagram and by calculation. This is the one I told you all about you're going to need a ruler for. When you do the ray diagram, you need to actually draw your lines to scale so you can then do an accurate, draw straight lines for your ray tracing. Come up with an as accurate as you can estimate of the, the image distance that they're asking for? Object distance. They give you the image distance. All right, well, let me get the boards cleared and we'll draw it up. When you do it on paper, you need to do it with a ruler. And if you don't have, does everyone have a ruler that they can use to do this with? But, I mean, at home, you have access to one. Okay, actually, we've got rulers in the room if you want to do this while we're here. Draw your baseline, your center line, through your lens. Now, here is your lens, and we can draw in the converging surfaces, the convex surfaces, if it helps you picture it. And then you measure over here 319 millimeters, or some scale of that. This is your image distance. So you can draw your image right here. It's a clear, focused image. And we know that the focal length for this is 215 millimeters. So we put that focal length on both sides, because for every lens, the focal length on one side is equal to the focal length on the other. Now, what we want to do is find where the object is placed. So we're going to draw 3 rays. The first ray is going to start from the tip of this. Well, all 3 will start from here at the head. The first one goes parallel to the axis at the lens it then curved, it is bent and now passes straight through the focal point and continues on. The second line you draw is from here through this focal point until it gets to the lens, at which point it turns and goes parallel. And then the final line you draw starts at the end point here and goes straight through the center of the lens. And those three lines should all intersect at a point on the other side of the lens. That is the position of your object. Now, you might be tempted to say, oh, this is an inverted object. You would be wrong to do so. The object, by definition, is always assumed to be upright. So in this case, the object is down. That means positive object is down, and the upright image that is formed over here is inverted relative to this object. Okay. If you wanted it to match the way you would normally have this drawn, you would have drawn an inverted object image and then traced the rays the other direction. Once you've done this ray tracing, making sure that all three of those lines intersect at a single point, or as close to a single point as you can make them, then you just measure this distance to the same scale, and there's your answer. Now, is this the part that was giving you a problem, or was the part B doing the actually calculating? Hey, what's the formula that we use?
Is it 1 over DO plus over D?
Yeah.
Equals
1 over F equals 1 over D sub I plus 1 over D sub O. And in this case, you're given F. So this is 1 over 215. And I don't know how many of you have noticed this or not, but when we're doing these equations, these formulas in millimeters or centimeters or meters, you don't need to convert them because it's all ratios. So as long as everything is specified in millimeters, you can write millimeters. If you want to convert them all to meters, you can do so. You can convert them to centimeters, but as long as they're all in the same units, it doesn't really matter. And we were not given the object distance, but we were given the image distance of 319 millimeters. So, 1 over 215 millimeters. Is that the focal length, 215? Yeah, and the image was not 319, 391. Sorry. So 1 over 215 minus 1 over 391 equals 1 over D sub O. You can hold your mouth right and punch the numbers into your calculator. Just 215 reciprocal plus 391 reciprocal equals reciprocal. You've got D sub O. Do we have any more questions from this homework assignment, from chapter 23? Any part of it you're not sure you've got a good grasp on yet? What about homework? Anyone has their homework ready to turn in?
You don't like little fringes?
No, I'll get rid of them. But I am thinking, I am thinking, I actually was about to say, I am thinking about next semester levying a fringe tax on the. I don't know how many of you have looked ahead. Our lab this week is on this very stuff, lenses, refracted optics. No, we're going to do like lenses on meter sticks and form real images, and I don't have any optical cables. Anyway, after the exam, we're going to be moving to, I forget the chapter number, but we're going to start looking at relativity and how, length contracts and how you can fit a 100-foot-long train inside a 50-foot-long tunnel. That kind of interesting, weird stuff.
So this is our last test, right?
This is the last test, it's not your last grade. So don't get the idea that you can start, sloughing off the rest of the semester.
So the last grade is going to be the next Tuesday for the lab, right?
The labs and the homework assignments, yeah.
So if I fail this test, that one that we took home would replace this year.
Oh yeah, except I don't really think you're going to fail this test. Yeah. No, not even close. Not for this one especially, because this one's going to be harder than any of the ones you've taken so far. At least in terms of the amount of problems you're going to have to solve. That's why I'm giving it as a take-home. Yeah. I really don't understand why. It seems like students in every class have the notion that the teachers are out to get you, that we're out to trip you up and to. I told you. Oh no! That has been posted on Canvas since day one of the semester. And you just happened to notice it.
Study for it.
Yeah, they sent the group chat like 11 o'clock. Yeah, we might just study tomorrow. Oh, God.
You do.
Like the group chat and Caleb was like, hey, is there a test? And everyone was like, I don't think so.
We want to sign in real quick.
Say again?
We need to sign in.
Yes, you definitely need to sign in. Would you pass a sign-in sheet around? Thank you. Now, yeah. 8 problems. This is a take-home exam, so I encourage you to work together. Obviously, it's open book. You will also notice that I only assigned even-numbered problems, so you actually have to work them. You can't just look up the answer and write it down. But you can work them together. Now, that said, does anyone else have any more questions out of chapter 23? And don't ask her about any of these problems.
So, what's number 10? 674, number 12 through 32. I don't understand those. We worked through those in class.
Let me ask you this. What are the sign conventions? Positive and negative. What sign would tell you, on what number would tell you whether an image is inverted or upright? The sign conventions. You know, where you what becomes negative, what becomes a minus, what gets a minus sign. What is the magnification of a lens system or a reflective mirror system? Exactly. Negative height, image height divided by object height. So, if M is negative, what does that tell you? No. If M is negative, then one of these has to be a negative sign and the other has to be a positive sign. No, I got that backwards. They have to both be the same. Either both are positive or both are negative, but they have to both be the same in order for M to become negative. If M is negative, then H of I is positive, and H sub O is also positive. Right? When you see H sub I is positive, what does that tell you? Because it's by definition, you always assume that H sub O is positive. The height of the object is always assumed positive. So if H sub I is also positive, what does that tell you? But what does that mean in terms of the optics? Exactly. When H sub I is positive, you have an upright image. If H sub I is negative, then you have an inverted image. That also means that if H sub I is inverted and it's a negative image, then minus H sub I over H sub O becomes a positive number, and your magnification becomes positive. So if you have a negative magnification number, you have an upright image. But look at H sub I to decide whether it's upright or inverted. What if D sub O is negative? What if, before I do that, let me ask you this. You've got D sub O and you've got D sub I. If D sub O is positive, it means that the object distance is positioned, the object is positioned on the same side of the lens that the light is coming from. On the side of the lens as the source light. If d sub I is positive, if the image distance is positive, I can get that inflection right. If d sub I is positive, that means that it is on the same side of the lens as the transmitted light. On the opposite side of the lens as the source light. Okay? So it's different from mirrors in that regard. A negative, if we were dealing with mirrors, a negative image distance would mean it's a virtual image. Okay. Here, a negative image distance. Boy, these things can get hard to say, huh? A negative image distance would still mean it's a virtual image, but it would be on the light side of the lens, not the transmitted side of the lens. So, as always, a positive image distance means a real image. A negative image distance means a virtual image. But in the case of transmitted light, in case of a lens as opposed to a mirror, that actually means the other side. Okay? This is your fundamental formula. And then you can sort out signs and directions from there. Any more questions? All right. You've got 20 more minutes to work on your exam before you have your next class, and your exams are due on Friday. Everybody sign the sheet? Good luck.